federated learning client devices can simultaneously upload their locally trained model to the server through the uplink norma, and it enables a spectrum efficient transmission for the multi-client local model. So it also addresses another challenging issue in the federated learning, as we mentioned before. So to enable this wireless power transfer for the federated learning, we propose three-phase procedures for this design. The phase number one is that the server uses wireless power transfer to sequentially transfer energies to the federated learning client. This is I use a three-client example, and the server using the wireless power transfer to sequentially charge number one, device number one, device number two, and device number three. And in phase number two, by using the collected energies from the wireless power transfer, each client device conducts a local model training and send its local model to the server. And phase number three is that the server aggregates and receives the local model to generate global ones. So there is essentially some trade-off in using the wireless power transfer for federated learning. At the positive side, wireless power transfer increases the power capacity of the end devices, which can improve their local training and uploading transmission, as I mentioned before. However, there's some downside. Number one is the wireless power transfer incur additional time overhead for performing the wireless power transfer, which again increase overall FL latency. In addition, wireless power transfer also incur additionally energy consumption for charging the end devices. So essentially, there's some trade-off between the overall FL latency and the total energy consumption. So this motivates us to consider a design trade-off, how to achieve a balanced FL performance between the overall latency and the energy consumption. So to this end, we formulate a mathematical optimization problem. And the first, we consider the end device, which is the FL client, the local training and uploading. We model each end device energy consumption for its local training, and end device energy consumption for uploading its local model to the BS through the NOMA, and the end device that harvest energy through the wireless power transfer. And eventually, we ask each device a total energy consumption, which can include the local training and including the local training and data transmission. Uploading the local model cannot exceed its harvest energy like this. And then we've modeled the base station energy models, the BS model aggregation and broadcasting. So the BS computational latency for its model aggregation is like this. Then the total energy consumption of the base station's energy consumption includes three parts. Number one is the base station or the server's total energy consumption for charging all devices in sequence through the wireless power transfer in this part, and the BS energy consumption for the model aggregation in this part, and the base station's energy consumption for its downlink transmission. It means that it will broadcast the aggregated model to all clients in the energy consumption in this one. So this is the three total energy consumption for the base station, and this is total energy consumption of the system. Then we consider the FL features, the training parameter, and overall latency. So in this work, we attune the parameters of each individual, the end device's local training accuracy. And based on the existing study, we know the average number of the local training at each device that can be expressed by a function of the local training accuracy like this. And then we know the average number of the global iteration in FL can be expressed by this expression as a function of the local training accuracy. And then we can express the end device's local latency for completed local training, depending on the number of local iteration and the latency for processing each individual training. Overall, the overall FL latency for each convergence is eventually given by this expression, including the latency for one single round of the iteration and the total number of the iteration, total number of the global iteration we need to perform before the convergence. So based on the previous modeling, we present a problem formation to minimize the total system cost. Like this one, we consider two parts. The part one is the total latency, and the second one is the total energy consumption. And the constraint is that for each individual end device, its total energy consumption cannot exceed its harvest energy in each single run, and the total energy consumption of the base station cannot exceed upper bound. So this problem is a joint optimization problem of the wireless power transfer decision for all the devices, for all the end devices, and all the end devices local uploading transmission via the NOMA transmission, and the base station or the servers downloading the transmission, and the server and end device the processing rate for local computing, and finally the FL, the global and local iterations. So this problem is a strictly non-convex problem, which is difficult to solve. So in this work, we propose a three-layer structure for solving the problem. And at the bottom layer, we aim at optimize the wireless power transfer decision for different end devices, and the BS and the server and the client processing rate at the bottom problem. And the middle problem, we aim at optimize the end client, the uploading, the end device, the uploading transmission time via NOMA transmission, and the BS BS downlink transmission, which is a broadcasting to all the end devices. And on the top layer, we optimize the federated learning, the global and local and iteration numbers. So eventually, this will work a top-down approach, solving the bottom problem, and then the middle problem and the top problem in a top-down layered approach to solve the problem. But because the time I think is limited, I'm not going to detail the algorithm. So eventually, I will go to the numerical result part. The first one is compare the advantage of NOMA assisted federated learning against some fixed local training accuracy scheme. So compared to the fixed local training accuracy, our proposed scheme can effectively improve the performance of the FL in terms of system cost and the computational time. And then we also compared our result with the federated learning because we're using NOMA. So we also compare the result with the federated learning using the conventional FDMA scheme, because NOMA improved the spectrum efficiency. So the results show that our proposed scheme can also again outperform the federated FDMA access scheme effectively. And then there are many studies nowadays using Broca coordinate descent method to solve complicated optimization problem. So in this work, we also using our proposed algorithm to compare with the BCD method. So because we are using the top-down composition approach, so our algorithm can achieve the global optimal solution for the original problem. However, the BCD method cannot guarantee to achieve the global optimal. So our proposed algorithm can outperform the conventional BCD problem. And then we also show the performance of demonstrated performance based of our algorithm based on the practical data set. We use the Mainston data set in this figure and the Cypher data set in this figure. Both results show that our result can outperform the performance. Even in the practical data set, our result can outperform the scheme with the fixed training accuracy. So finally, let's see the conclusion and the future direction. So in this work, in this talk, I present the motivation on the benefit of integration wireless power transfer for federated learning. And we propose a framework of building the wireless power transfer assisted federated learning in which the FL server using the wireless power transfer to charge the end devices, such that the end devices can have the sufficient energy supply for their local training and uploading transmission. To study this problem, we formulate a joint optimization of the wireless power transfer for different clients, and the client is the NOMA transmission, and the BS the broadcasting transmission, and the client and the BS the servers processing rate for model training and model compute aggregation. And of course, also the FF training parameters Our goal is to minimize the assistant cost function, which balance energy consumption and FLA convergence latency. We also design a layered algorithm for efficiently solving the formatted non-convex optimizing problem. Regarding the future direction, I think there are threefold the future direction. Number one is that because the performance of wireless power transfer strongly depend on the quality of channels. So the next job our work is to use the IRS, which is the intelligent refracting service, to improve the effective quality of the radio channel, so that the end client can collect more energy through the radio channel in the wireless power transfer. The second one is that in our current work, we just consider one single server. So the next step is that we will consider more servers, which is a multiple server FL with a hierarchy structure. And last but not least is the age of information aware user schedule, because in the federated learning, the local training takes time. So after the end client to complete the local training, this is a local model is some kind of the out of the state. So we are going to introduce the AOI information into the federated learning, so that to improve the freshness of the distributed training procedure. So I think this is the end of my talk, and this is my personal page. This is my email address. And if you have any question, you are very much welcome to contact me.